Welcome to this video lab where we're going to be performing an experiment concerning titrations. The purpose of this experiment is to perform a series of titrations to determine the concentration of an unknown solution of hydrochloric acid and to determine the buffering capacity of a buffered acetic acid solution. In this lab, we'll learn how to properly condition a burette. We'll determine the precise concentration of an unknown HCl solution by titrating it with a standardized sodium hydroxide solution. The experimental pKa of acetic acid will be determined by calculating the half equivalence point of a titration with acetic acid and sodium hydroxide. And lastly, we'll determine the buffering capacity of a buffered acetic acid solution by titrating it with sodium hydroxide. Before we dive into the lab itself, let's first discuss a bit of background related to the experiment. An acid is a compound that dissociates in water to produce hydronium ions, and a base is a compound that dissociates in water to produce hydroxide ions. The strength of an acid or base is entirely dependent on the amount of dissociation. Strong acids and bases will dissociate completely in solution, whereas weak acids and bases only partially dissociate. For acids, we attribute an acid dissociation constant, Ka, that tells us the ratio of dissociated species in solution. A larger Ka value is associated with a stronger acid, and a smaller Ka value associated with weaker acids. For bases, there is a similar dissociation constant, Kb. Common strong acids include compounds like hydrochloric acid, sulfuric acid, and nitric acid. Common weak acids include compounds like acetic acid, carbonic acid, and phosphoric acid. Titrations are an analytical technique used to quantify the amount of species in a solution by reacting it with another species of a known concentration. Acid-base titrations monitor the pH of a solution over the course of a neutralization reaction to find the original concentration of the unknown. Some titrations utilize an indicator, which is an organic dye whose color is directly dependent on the pH of the solution. This lab will utilize the dye phenolphthalein, which changes from colorless to pink at around pH 8.2. A pH probe is an instrument that monitors the precise pH of a solution. It utilizes a sensitive glass electrode that measures a voltage that can change depending on the concentration of hydronium ions in solution. The measured voltage is converted and displayed as a pH measurement. In a titration, the equivalence point is when there is a stoichiometric amount of titrant added to completely neutralize the analyte solution. The point is determined mathematically and cannot be precisely measured experimentally. The endpoint of a titration, however, is when the indicator changes color and shows when a neutralization reaction has stopped. Buffers are any solution that resists dramatic changes in pH upon the addition of an acid or a base. A buffer is always made with two components, either containing both a weak acid and its conjugate base, or containing a weak base with its conjugate acid. We can relate the pH of a buffered solution to the concentrations of each buffer component using the Henderson-Hasselbalch equation. In the equation, we see that the pH of the solution is equal to the pKa plus the log of the ratio of the concentrations for the conjugate base and weak acid. From the Henderson-Hasselbalch equation, we can also see that when the concentration of the weak acid and the conjugate base are equal, the second term cancels, meaning that the concentrations are the same and the pH is equal to the pKa. Buffers resist changes in pH by neutralizing the added species, and we define the extent that a buffer can resist changes in pH by its buffering capacity. Specifically, the buffering capacity is defined as the number of moles of strong acid or strong base needed to change the pH of 1 liter of buffer by 1 pH unit. Now that we've discussed the background of the lab, we can discuss some of the safety concerns for this experiment. In this lab, we use various acids and bases such as hydrochloric acid, sodium hydroxide, and acetic acid, which are all corrosive to flesh and can cause skin burns, so gloves should be worn at all times during the experiment. With that out of the way, let's start the experiment. To start the experiment, we acquire 15 milliliters of our unknown HCl solution before preparing the lab quest for data collection. To prepare the lab quest, we plug in the pH probe to channel 1, select Sensors, Data Collection, and then set the data collection mode to Events with Entry. We set the axis name to volume, and we have units of milliliters. Now that the lab quest is ready, we can set up the titration. First, we will prepare the solution that we'll titrate into. In a clean 250 milliliter beaker, we add approximately 75 milliliters of water. The exact volume doesn't matter for the water, but for the unknown hydrochloric acid, we need a highly accurate volume. Therefore, we measure the 5 milliliters of the unknown HCl sample with a 5 milliliter volumetric pipette. We also add just a few drops of our phenolphthalein indicator and a stir bar before placing it on top of the stir plate. Next, we condition and prepare our burettes for the titration. To condition a burette, we use a funnel to add a small amount of liquid to the top. Then, using a gloved hand, we cap the top of the burette with a thumb and gently invert the burette multiple times to rinse all of the internal surfaces of the glassware. Lastly, we drain a small amount of the solution through the tip before discarding the conditioning liquid. To properly condition the burette, we rinse it twice with deionized water, and then twice again with 2 small aliquots of our titrant solution. Conditioning is important to ensure that the titrant solution does not get diluted or contaminated by previous water or reagents inside the burette. After conditioning twice with water and then twice with our 0.5 molar sodium hydroxide, we fill up the burette to somewhere near the top, anywhere between the 0 and the 5 milliliter mark. After removing the funnel and placing the burette on the burette stand, we record the initial volume of the burette to the nearest 0.05 milliliter mark. Note that the graduations on the burette are read in the opposite direction of those on a graduated cylinder. The reading for this initial volume is 0.25 milliliters. Next, we prepare the pH probe for the measurement. The pH probes are stored in a specific solution to prevent them from drying out. To remove the pH probes from the bottle, we first unscrew the cap to open the vial, and then gently pull the cap from the pH probe. When handling the pH probe, it's important to keep it in a solution to prevent the sensor from drying out. We gently rinse the pH probe over a waste beaker before securing the pH probe into our titration setup. With this, we're ready to perform the titration. With the stirring on, we first perform a fast run to determine the approximate volume of when the endpoint is reached. To do this, we add sodium hydroxide relatively quickly until the solution turns and remains a pink color. After the solution turns pink, we record down the volume on the burette and calculate the endpoint volume. In this case, the final burette reading was 11.00 milliliters. This makes our endpoint at 10.75 milliliters. After completing the fast run, we dispose of the reaction mixture into the waste and re-prepare the unknown HCl solution for the actual titration. Same as before, we add approximately 75 milliliters of water before using a volumetric pipette to add 5 milliliters of the unknown HCl solution, followed by a few drops of the phenolphthalein indicator dye. After placing the freshly prepared HCl solution onto the hot plate and setting up the pH probe, we can perform the full titration. To start the titration, we begin collecting data on the LabQuest, and we collect the first data point, entering 0 milliliters. Next, using the burette valve, we carefully add 2 milliliter increments of titrant until about 3 milliliters below the endpoint, while recording the burette volume and pH upon each addition. As we approach the endpoint, we reduce the amount of titrant added between each data point from 2 milliliters to 0.5 milliliters, and then finally down to dropwise additions. We continue adding dropwise additions of titrant until the HCl solution turns pink and remains that color. This volume is the end point. After reaching the endpoint, we add 2 half milliliter portions, followed by 2 1 milliliter portions, and then another 2 2 milliliter portions of titrant. This end of the curve is to ensure that we have enough data points for calculating the second derivative curve. Once finishing the titration, the pH probe is removed, rinsed with water, and then properly stored. The reaction mixture is disposed of in a waste beaker, and now that our titration is complete, we can move on to Part B. To start Part B, we prepare 50 milliliters of a 0.05 molar acetic acid solution from a 0.5 molar stock solution. Using a graduated cylinder, we measure out 45 milliliters of deionized water into a clean 150 milliliter beaker, and then measure out 5 milliliters of 0.5 molar acetic acid and add that to the water. Next, we prepare 100 milliliters of 0.05 molar sodium hydroxide from a 0.5 molar stock solution. We do this by first measuring out 90 milliliters of deionized water, and then adding 10 milliliters of 0.5 molar sodium hydroxide stock solution. To prepare the titration, we first have to pour out the old solution in the burette and recondition it with our new titrant. So first we rinse the burette with 2 small portions of deionized water, followed by 2 small aliquots of our freshly prepared 0.05 molar sodium hydroxide. After conditioning, we fill the burette to the top and record the initial burette reading. Finally, before performing the titration, we prepare the solution that we'll titrate into by measuring approximately 50 milliliters of deionized water into a 250 milliliter beaker. Then, using a 10 milliliter volumetric pipette, we add 10 milliliters of the prepared 0.05 molar acetic acid solution. Next, we add a stir bar, place the beaker on the hot plate, set up the burette and pH probe, and begin data collection. Same as the Part A titrations, we begin by recording down the initial burette reading and then collecting the first data point at 0 milliliters of titrant added. We start adding the titrant in approximately 2 milliliter increments until the pH of the solution has increased to around 5 or 6. We record the data points between each addition. As we approach the equivalence point, we decrease the amount of titrant added between each data collection point from 1 milliliter to half a milliliter, 0.2 of a milliliter, and then finally to dropwise additions. After reaching the equivalence point, we add a further 6 half milliliter portions, recording the pH each time to finish out the titration curve. With that, the titration is complete. We clean up, rinse off the pH probe, and dispose of the reaction mixture into the waste beaker before moving on to Part C. To start Part C, we first prepare 30 milliliters of a buffered 0.25 molar acetic acid solution. To a clean 100 milliliter beaker, we measure as close to 1.021 grams of solid sodium acetate trihydrate. Next, using a graduated cylinder, we measure 15 milliliters of deionized water and add that to the beaker. Finally, we measure 15 milliliters of 0.5 molar acetic acid and add that to the beaker before thoroughly mixing with a glass stir rod. Next, we prepare 50 milliliters of 0.25 molar sodium hydroxide solution by measuring 25 milliliters of deionized water into a clean beaker, followed by 25 milliliters of 0.5 molar sodium hydroxide stock solution. Next, we prepare the burette for the titration by discarding the excess titrant from part B and reconditioning the burette twice with water and then twice with the freshly prepared 0.25 molar sodium hydroxide solution. Lastly, before we perform the titration, we have to prepare the buffer solution that we're going to titrate into. We measure approximately 50 milliliters of water into a clean 250 milliliter beaker, and then, using a 10 milliliter volumetric pipette, we measure 10 milliliters of the previously prepared 0.25 molar buffered acetic acid solution. Finally, we add a stir bar, place the beaker on top of the hot plate, and then set up the burette and pH probe to begin data collection. Same as before, we start the titration by recording down the initial burette reading and then collecting the first data point at 0 milliliters. This time we add repeated approximate half milliliter portions of titrant, recording the burette volume and pH at each time until the pH of the solution starts to change dramatically. We decrease the volumes added as we approach the equivalence point, and then once it's been reached, we add 6 half milliliter portions to finish off the titration curve. After this, we clean up, remove the pH probe, and discard the reaction mixture into the waste beaker before moving on to part D. For the last part, we prepare 50 milliliters of 0.25 molar hydrochloric acid by measuring 25 milliliters of deionized water into a 100 milliliter beaker, followed by 25 milliliters of 0.5 molar hydrochloric acid stock solution. We again have to re-prepare the burette with our new titrant, so we dispose of the old solution, and then recondition the burette twice with deionized water, and then twice with 2 small aliquots of our freshly prepared 0.25 molar hydrochloric acid solution. Next, we prepare the buffer solution that we're going to titrate into by measuring approximately 50 milliliters of deionized water into a 250 milliliter beaker. Then, add 10 milliliters of the 0.25 molar buffered acetic acid solution we prepared at the start of Part C, using a 10 milliliter volumetric pipette. Lastly, we add a stir bar, place the beaker on the hot plate, and then set up the burette and pH probe to begin data collection. This titration is performed the same as Part C. We record the starting point, and then repeatedly add half milliliter portions of titrant, recording the pH each time. After reaching the equivalence point, we add another 6 half milliliter portions, recording each time to finish off the titration curve. Now we clean up since we're finished with Part D. We rinse off the pH probe and properly store it back in its storage bottle. All the excess solutions are poured into the proper waste container, and the burette and other glassware are rinsed thoroughly. With this, the experiment is finished. We've successfully recorded 4 titrations. A strong acid, strong base titration to determine the concentration of an unknown HCl solution, a titration between acetic acid and sodium hydroxide to determine the pKa of acetic acid. Then lastly, 2 buffered acetic acid titrations, one with a strong base and one with a strong acid. Thanks for watching.